But this is basically my proposal for my research. So that's the motivation. Oh, sorry, backtrack a bit. The reason why I'm interested in this is that, again, in computer graphics, you have lots of research on geometry. You have lots of research on rendering, basically dealing with 3D virtual world, right, in order to create images. So that is a lot of literature that have been, so many people have done research on this before. So it feels like there must be something that we can learn from computer graphics to help the vision models understand the 3D world. So that was my inspiration. So that was the motivation. So now I'm going to talk about my first project, which is RenderNet, which is basically learning how to render. Instead of handcrafting all the simulation things like that, the question is, can a neural network learn to render from scratch? The next part is the HoloGAN paper. It's still currently under review. It's basically extending RenderNet in the context of a generative model, and finally a conclusion. So let's talk about RenderNet, a deep CNN for differentiable rendering. So why is differentiable rendering useful for vision? You can imagine that if I give you an image, again, of a face, and now you have to guess the input, like all of the underlying 3D model and texture of that image to recreate the image, right? The best thing you can do is that you start to have some guess. You try to compare your output with the image you're trying to recreate, compute the difference between them, and take a step towards the gradient of the basically doing optimization, where you want to minimize the difference between the image you currently have and the image you want to recreate. So if you can if you can guess an input that can perfectly recreate this image that you want to recover, then that is what you want to recover. But again, because right now all of the rendering pipelines are indifferentiable, that's why you cannot use this very powerful computer graphics rendering, ray tracing, something like that, in vision right now. You cannot do that right now. So it is a very active area of research. So the first one that's kind of like starting this storm of differentiable rendering is OpenDR by Loper and Black from the MPI Tübingen. And this more to recently work are, again, trying to solve differentiability by approximate the gradient. So if you have a function that you can, differentiate, there are two ways to try to get around the problem. The first way is you try to, so you have the step function, right? You cannot differentiate. So the first way to get around it is that you kind of soften the gradient, so you try to approximate the gradient. So that's the first one. The second way of doing it is that you try to come up with an approximated function with the step function, but itself is differentiable. Does that make sense? So it's kind of like differentiable by design, by making like a surrogate differentiable, or you're trying to directly approximate the gradient. So that's what's happening with all of these methods. The problem is, they are, in a way, they are, this rendering are not used, so they are all handcrafted. And because they are handcrafted, they are stuck with a particular type of rendering. So I told you there are two kind of main methods, rasterization and ray tracing in the previous lecture. So the top ones are rasterization, differentiable rasterization. The bottom one is differentiable ray tracing. But they're kind of like stuck in that handcrafted domain. So it's not versatile enough. And this guy, because it's trying to approximate ray tracing, is also quite slow right now to do anything useful. So if you want to train a model, and for each update step, it takes like 2 minutes to update, then it will take forever to train a model. So those are the current state of the art. So before I move on to present RenderNet, I want to remind you of two main points. Again, when when you want to do rendering, there are two important steps. The first one is to compute visibility, which is whether this object is in the scene or not. And the second one is compute shading, like how does the object look like in this image, given this lighting, given this material, how will the object look like in the image? Those are two steps. Another thing that I want to highlight, is doing rotation with CNN is super hard. This goes back to the point that I just made about how the current models cannot do with rotation so well. But it also comes down to the fact that in order to present a rotation matrix, is basically we use a bunch of sine, cosine, right? In order to approximate sine and cosine using a neural network, it's actually very expensive. It can be done, but it's very inefficient. But from a human point of view, it's super easy. We learned it from 3rd grade, right? Not bad, huh? Sine, cosine, I don't know. And also, okay.
Lớp 6 viên. Lớp 6, lớp 7.
Dạ, hồi xưa bị bắt đi học thêm rồi. Anyway, nói chung là sine cosine đối với for human is super straightforward, right? Just literally a 4x4 matrix. So it seems like it's a waste to force the network to learn something that we already know so well and can implement so well. So it's literally a 4x4 matrix multiplication, right? So these are the insights that we use when we design RenderNet. So RenderNet is a rendering pipeline. So it does what rendering does. It takes in a 3D model, a lighting, a camera, and return an image. Okay. The difference is that all of the rendering part is learned from scratch. And unlike other works that I've shown you, we do the camera, so if we have a chair right here and we want to look at it from different poles, like we want to look from here or there, instead of forcing the network to learn this transition from scratch, because it's really hard, we just hard code it in directly. So it's literally, I implement a 4x4 matrix multiplication for that model and transform it to the desired pose. I don't want the model to learn that, so that it can use all of the remaining capacity to learn the actual rendering part, which is the most important part. So I won't go through them in details, but basically it comprises of 3 parts. The first part is 3D convolution, so it's a series of 3D convolution with downpolling to learn 3D features. Because one thing that one thing that you have to think about when you do rendering is that depends on the camera model that you're using, the perspective can change a lot, right? I mean, you take the same photo of the same person with a Samsung phone and an iPhone that are completely different. That depends on the camera model.
Can you explain about the input of this model? About light position and camera pose, like input?
So, so the 3D model is assumed to be in the canonical pose, the input. So that's one assumption. The camera pose is literally, so you're doing this in camera space, but you can understand is that if I stand here, the camera pose is the location of camera in relation to the object. So you can take